Before there was light, before there was darkness, before the first tick of time or the faintest whisper of space, there existed something physicists call the quantum void. This was not emptiness in the way we usually think of it, not a dark room waiting to be filled, but rather a state of pure potentiality so profound that our everyday language struggles to contain it. Scientists studying quantum field theory have discovered that what we call empty space is never truly empty, but filled with fields that permeate all of existence, flickering with temporary energy borrowings, too brief for time itself to register. Imagine trying to describe the concept of silence to someone who has never heard sound, or attempting to explain stillness to someone who has never experienced motion. This is the delicate challenge we face when we try to speak about what came before our universe began. The quantum void was not a place you could visit because there was nowhere to go to. It was not a moment you could point to on any timeline because there was no one yet to mark or measure. What physicists sometimes call the quantum vacuum state represents a kind of baseline reality where the laws of physics as we know them hover in pure potential, not yet activated, not yet expressed in the intricate dance of particles and forces that would later fill the cosmos. Float here for a moment with this idea. In this state before states, energy itself existed in a form that stretches our understanding. Research in quantum mechanics reveals that particle-antiparticle pairs can spontaneously appear and disappear in intervals as brief as 10 to the negative 44 seconds, a phenomenon called quantum fluctuation that occurs constantly throughout the universe, even today. These fluctuations are not like waves rippling across water or vibrations traveling through air, but rather represent temporary borrowings from the fabric of possibility itself. A particle and its antimatter twin might flicker into existence for an interval so brief that time itself hardly registers the event, then immediately annihilate back into the underlying field from which they emerged. The temperature of this pre-universe state, if we can even meaningfully apply that familiar word, stretched beyond comprehension. Thermal energy, as we understand it, requires particles to move through space and collide with one another, transferring momentum in ways that we can measure with our instruments and feel on our skin as warmth or cold. But before there were distinct particles, before there was motion through space, before the fundamental separation of here from there that allows collision and interaction to occur, what would heat actually mean? Perhaps it serves us better to imagine this primordial state as somehow containing all possible temperatures at once, compressed and collapsed into a single point of pure, undifferentiated potential. Let your awareness rest gently with this paradox. The four fundamental forces that would later govern every interaction in the universe we inhabit began as a single unified force. Gravity pulls matter together across vast distances. Electromagnetism lights our world and binds atoms into molecules. The strong nuclear force holds the hearts of atoms together against enormous pressure. The weak nuclear force allows certain particles to transform and decay. Studies of grand unified theories suggest that at energies above approximately 10 to the 15th billion electron volts, these seemingly different forces merge into one, behaving identically in ways that our current particle accelerators cannot yet directly test. You might picture white light before it passes through a glass prism and separates into the rainbow spectrum of distinct colours, each beautiful and unique. In the same way, this unified force contained within itself all the future richness and complexity of physical law. All the intricate rules that would eventually allow atoms to assemble, stars to ignite and burn for billions of years, planets to form and cool. The symmetry of this unified state was perfect and unbroken, representing a kind of cosmic simplicity that our universe has been gradually moving away from ever since its first moment of existence. In physics, symmetry represents a kind of sameness or invariance, a situation where changing your perspective or transforming a system in certain ways leaves everything fundamentally unchanged. Breathe softly into this moment of perfect balance. The early universe possessed this quality in its most extreme and beautiful form. There was no preferred direction in space because space itself had not yet unfurled. There was no distinction between past and future because time had not yet begun its one-way flow. Emmy Noether proved in 1918 that every symmetry in physics corresponds to a conservation law. So this perfect early symmetry meant that certain properties of the universe would remain constant even as everything else changed. The forces were indistinguishable from one another because the energy scale was so extraordinarily high that their individual characteristics had not yet emerged from the unified whole. Scientists exploring the physics of this earliest possible time work at the very edge of what our current theories can describe. General relativity. Einstein's geometric theory of gravity describes how mass and energy curve the fabric of space-time. It works beautifully for describing planets orbiting stars, light bending around galaxies, even the expansion of the universe itself. But general relativity begins to struggle when we try to apply it to conditions of infinite density and temperature. Quantum mechanics, our astonishingly successful framework for understanding the behavior of particles and fields at the smallest scales, runs into its own difficulties when we attempt to incorporate gravity into its mathematical structure. Allow yourself to drift with this mystery. This gap in our understanding, this place where our two most fundamental theories seem to point towards something beyond themselves, is where physicists hope to find a more complete theory. Something that might be called quantum gravity. Several approaches have been proposed over the decades, each offering its own perspective on what might have existed before the conventional beginning of time. String theory suggests that the most fundamental constituents of reality are not point-like particles, but rather tiny vibrating loops of energy, each only about 10 to the negative 35 meters long, existing in a space with more dimensions than the three we directly experience. Loop quantum gravity takes a different approach, suggesting that space itself has a discrete structure at the smaller scales. Research by Abhay Ashtekar and others indicates that space might be composed of indivisible units of volume, each roughly 10 to the negative 99 cubic centimeters, which might allow us to describe the very beginning without running into mathematical infinities that plague other approaches. In this view, space has a kind of granular texture at scales far too small to observe directly. Some theoretical physicists have explored the possibility that our universe emerged from a previous state through a quantum tunneling event, similar in principle to the way particles can sometimes appear on the other side of energy barriers that classical physics says they should never be able to cross. rest here in the space between what we know and what we wonder. In this scenario, what we call the beginning of our universe might actually represent a transition from one quantum state to another. A spontaneous fluctuation in the quantum vacuum that somehow gave birth to expanding space, flowing time, and all the matter and energy that would later form everything we see. The mathematics describing such an event is delicate and speculative, reaching toward truths that may lie forever beyond our ability to test directly. Other researchers have considered whether time itself might be an emergent property, something that arises from more fundamental timeless laws operating at the deepest level of reality. Carlo Rovelli and others working in quantum gravity have proposed models where time does not exist at the most fundamental level, but emerges from the interactions of quantum systems, much like temperature emerges from the motion of many molecules. In this view, the quantum void might exist in a kind of eternal present, with no before or after, while the universe we inhabit represents a particular solution or realization of these deeper laws, one where time flows and entropy increases and cause precedes effect. This is deeply counterintuitive, since our entire experience is built around the passage of time, the clear distinction between memory and anticipation, between fixed past and open future. Let the strangeness of this wash over you gently. The concept of nothing itself becomes slippery and uncertain at these extreme boundaries of physics. Philosophers have long pondered why there is something rather than nothing, and physicists approaching this question discover that nothing may be far more complicated than simple absence. Even the quantum vacuum, often described as empty space, teems with virtual particles and quantum fluctuations. Heisenberg's uncertainty principle, formulated in 1927, tells us that energy and time cannot both be precisely determined simultaneously, allowing temporary violations of energy conservation for time intervals so brief that nature does not seem to notice or care. This dynamic fluctuating void may represent the closest thing to nothing that physics allows, yet it is already rich with structure and potential. In this quiet moment before moments, the universe rested in pure potential. There were no stars yet to burn, no galaxies to spiral through space, no planets to orbit or cool, no chemistry to build complexity, no life to wonder. Yet somehow woven into the mathematical structure of fields and forces in this pre-universe state lay all the future richness of cosmic evolution. Settle into the quiet promise of what has not yet begun. The hydrogen that would later fill space and slowly condense into the first stars was already implicit in the rules governing how fields would behave once space began expanding. The carbon that would form in the hearts of dying stars, the oxygen that would allow worlds like ours to support life, the intricate periodic table of elements. All of this was already present as potential consequence, waiting for the universe to cool enough that these patterns could manifest. You may imagine this primordial state not as a void in the conventional sense, but as a kind of cosmic seed, dense with compressed possibility. If you could somehow exist in that instant before time began its flow, you would not see darkness or light. You would not feel heat or cold. You would not experience the passage of seconds or the extension of space in any familiar direction. Paul Dirac's work on quantum field theory in the 1930s showed that what we perceive as empty space is actually the lowest energy state of quantum fields, suggesting that even nothingness has structure and properties. Instead, you might sense, if sense is even the right word, a kind of balanced tension, a poised readiness. Allow yourself to rest in this tension that holds everything. The questions that arise when we contemplate this pre-beginning state are among the deepest and most beautiful that humans can ask. What selected the particular laws of physics that govern our universe rather than some other set of rules? Why does our cosmos have 3 dimensions of space and one of time rather than some other configuration? What determined the values of the fundamental constants? Numbers like the speed of light at 299,792,458 meters per second, the strength of gravity, and the mass of the electron, that seem arbitrary yet make an enormous difference to how the universe evolves. These questions do not have answers yet and may never have answers in the conventional sense. Yet asking them brings us to the very edge of what consciousness can contemplate, where science and philosophy and wonder all converge. As we rest here, considering the universe before it was a universe, we might feel a sense of curious peace. The cosmos that would unfold from this pregnant void would become unfathomably large and ancient, filled with trillions of galaxies and more stars than humans could count in thousands of lifetimes. Float in the space before beginning. Yet it all began from this, from a state so simple and unified that it contained no complexity yet, no structure yet, no separation yet between the forces and fields that would later create such astounding variety. The second law of thermodynamics tells us that entropy, the measure of disorder, always increases over time in closed systems. Yet the early universe possessed extremely low entropy, despite its apparent chaos, a puzzle that physicists are still working to fully understand. In a sense, the entire history of the universe represents a journey from simplicity toward complexity, from unity toward diversity, from perfect symmetry toward the broken symmetries that allow interesting things to happen. The quantum void before the beginning was not lonely or cold, because loneliness and cold are experiences that require contrast, require something else to compare against. It simply was, existing in its own complete and self-contained way, neither waiting nor not waiting, neither stable nor unstable. Until the moment, if moment is even the right word, when something shifted. When the unified force began to separate. When space began to expand. When time began its irreversible flow forward. When the universe as we know it burst into existence and began its long, slow journey toward stars and planets, and eventually toward minds that could look back and wonder about their own origin in that first instant of becoming. Rest now in the quiet before creation. In the inconceivably brief interval that physicists call the Planck time, something extraordinary occurred. This duration, approximately 5 times 10 to the negative 44 seconds, represents the smallest unit of time that has any meaningful physical significance according to our current understanding. Max Planck derived this fundamental timescale in 1899 by combining the speed of light, Newton's gravitational constant, and the quantum of action into a single natural unit that appears to set a limit on how finely we can divide time. To put this in perspective, there are more Planck time units in a single second than there have been seconds since the universe began. In this almost unimaginably short interval, the universe transitioned from the quantum void we explored earlier into something recognizable as space-time. Though still utterly alien to anything we encounter in our daily lives. At this earliest stage, the universe was compact beyond comprehension, with all of space compressed into a volume smaller than a single atom, smaller even than the nucleus at an atom's heart, smaller than any particle we have ever detected in our most powerful accelerators. Yet despite this incredible compression, this tiny volume contained all the energy and potential that would eventually expand into the observable universe we inhabit today. Allow this scale to wash over you softly. The density of the universe in this first instant was so extreme that our usual concepts of matter and energy begin to blur together, becoming different aspects of the same fundamental reality described by Einstein's famous equation, linking mass and energy. Albert Einstein showed in 1905 that energy equals mass times the speed of light squared, meaning that sufficiently high energies, mass and energy, become freely interconvertible. The temperature at this earliest time reached values that make the centers of stars seem cold by comparison. While the core of our sun burns at around 15 million degrees, and the most intense processes we can observe in the contemporary universe might reach trillions of degrees, the temperature in the first Planck time approached 10 to the 32nd power degrees. At such temperatures, particles could not exist in any stable form. The distinction between matter and antimatter, between particles and the fields from which they arise, between energy and mass, all these familiar categories become fluid and interchangeable. In this extreme environment, the unified force that had characterized the quantum void began to undergo its first separation. Gravity, the force that shapes the large-scale structure of the universe, pulling galaxies together and guiding planets in their orbits, started to become distinct from the other fundamental forces. Let yourself float through this first separation. This separation, called symmetry breaking by physicists, represents one of the most important moments in cosmic history. Before this transition, the universe was more symmetric, more uniform, with no meaningful difference between what we now recognize as distinct forces. After this transition, gravity split off and began to follow its own rules, while the other forces remained unified for a bit longer. The mechanism behind this symmetry breaking involves concepts from quantum field theory that stretch our intuition. Imagine a perfectly round ball balanced precisely at the peak of a hill, representing the symmetric state where all forces are unified. Research by Peter Higgs and others in the 1960s showed that certain quantum fields can have multiple stable states, and the universe can transition from a symmetric high-energy state to an asymmetric low-energy state through spontaneous symmetry breaking. This configuration is unstable in a particular way. The slightest perturbation, even just a quantum fluctuation, might cause the ball to roll down the hill in some direction. Once it begins rolling, the symmetry is broken because now there is a preferred direction, the direction the ball rolled, whereas before all directions were equivalent. drift gently with this image of rolling and settling. In a somewhat similar fashion, the unified force field that permeated the early universe underwent a transition, where it rolled into a new configuration, one where gravity was distinct and began to interact with space-time in the characteristic way we observe today. This separation of gravity from the other forces had profound consequences for how the universe would evolve. Gravity is unique among the forces in that it couples to energy itself, causing space-time to curve in response to the presence of matter and energy. John Wheeler famously summarized general relativity by saying that matter tells space-time how to curve, and curved space-time tells matter how to move. This creates an elegant feedback loop that governs everything from the fall of an apple to the orbit of planets to the expansion of the universe itself. In the language of general relativity, gravity is not really a force at all in the conventional sense, but rather an effect of curved geometry. As gravity separated and became distinct, space-time itself began to take on more definite character. Before this moment, the quantum nature of reality dominated so completely that even the geometry of space and time was subject to quantum uncertainty and fluctuation. Rest in the emergence of shape from shapelessness. Space and time were not smooth and continuous, but rather foamy and uncertain at the Planck scale, with the very topology of space-time fluctuating from moment to moment. John Wheeler introduced the concept of quantum foam in the 1950s to describe how space-time might fluctuate wildly at the smallest scales, with wormholes and topology changes occurring constantly in a seething microscopic chaos. After gravity separated and the universe expanded even slightly beyond the Planck scale, space-time became more classical, more like the smooth geometric arena that Einstein described, though still influenced by quantum effects from the matter and energy it contained. The expansion of space itself, which would continue to the present day and beyond, began in earnest during these first instants. It is important to understand that this expansion is not like an explosion where matter rushes outward through pre-existing empty space. Rather, space itself is stretching and growing, carrying matter and energy along with it. Galaxies in the distant universe are moving away from us not because they are traveling through space, but because the space between us and them is continuously increasing. Allow this distinction to settle gently in your mind. This distinction becomes especially important when we think about the earliest moments, because there was no outside for the universe to expand into. Space itself was expanding, creating more space, increasing the distance between any 2 points. Edwin Hubble discovered in 1929 that distant galaxies are receding from us at speeds proportional to their distance, providing the first direct evidence that the universe is expanding and implying that it must have been smaller and denser in the past. You may picture the early universe as being filled not with particles in the way we usually think of them, but with intensely energetic fields rippling and fluctuating, sometimes briefly coalescing into particle-like excitations that would just as quickly decay back into pure energy. The quantum fields representing the electromagnetic force, the strong nuclear force, and the weak nuclear force were all present, still unified into a single electroweak strong force at this early stage, but beginning to differentiate. These fields carried enormous energy densities, and their interactions governed how the universe behaved and how fast it expanded during these first moments. The concept of time itself requires some careful thought when we consider these earliest instants. Drift into the strangeness of early time. In our everyday experience, time flows smoothly and continuously, providing a universal clock that allows us to say when events happen and in what order. But in the regime where quantum effects are important, time becomes more subtle and uncertain. At the Planck scale, our usual notion of a smooth, continuous timeline breaks down, replaced by something more granular, or perhaps more probabilistic. Some approaches to quantum gravity suggest that time itself emerges from more fundamental timeless laws, meaning that at the very beginning there might not have been a clear sense of before and after in the way we usually understand it. Despite these conceptual challenges, physicists have developed mathematical frameworks that allow them to describe what likely happened in the first Planck time with reasonable confidence, at least in broad outline. The universe began with all four fundamental forces unified: extremely high energy density and extreme curvature of space-time. As the universe expanded and cooled, even if only slightly at first, gravity separated out, followed by the other forces in sequence. This process released energy and drove further expansion, creating a kind of feedback where expansion allowed cooling, cooling allowed forces to separate, and forced separation released energy that drove more expansion. Let this cycle wash through you like breath. The quantum fluctuations that occurred during this earliest time would have profound consequences much later. At the Planck scale, random quantum variations in the energy density of different regions of space were inevitable, required by the uncertainty principle that lies at the heart of quantum mechanics. Stephen Hawking and others showed in the 1980s that quantum fluctuations during the earliest moments would be stretched by cosmic expansion and eventually become the seeds of galaxies and large-scale structure. These tiny variations, initially far smaller than an atom, would be stretched by the subsequent expansion of the universe until they became the seeds of all cosmic structure. Billions of years later, gravity would amplify these tiny density differences, causing matter to clump together slightly more in some regions and slightly less in others, eventually forming the web-like pattern of galaxies and voids that we observe in the large-scale structure of the universe today. As we rest with these ideas, we might sense the almost dreamlike quality of this earliest time. The universe was not yet a place where anything familiar could exist. There were no atoms, no particles as we know them, no chemistry, no possibility yet for complexity or structure. Breathe into the simplicity of pure becoming. Instead, there was pure energy in its most concentrated form, fields vibrating and interacting according to fundamental rules, space expanding and cooling, time beginning its flow. The four forces that would govern all future interactions beginning to separate and take on their distinct characters. In a sense, the universe was being born not as a thing, but as a process, a dynamic unfolding governed by mathematical laws that we are still working to fully understand. The fact that our universe exists at all, that it emerged from the quantum void and began expanding rather than collapsing back into nothingness, involves some subtle physics that researchers continue to explore. In principle, a universe could have been born and immediately collapsed, or could have expanded for a moment and then recollapsed, never lasting long enough for stars or galaxies or life to develop. Andre Linde and others have calculated that only universes with very specific properties, including a nearly flat geometry and particular force strengths, can survive long enough to develop interesting structure. The particular balance of energy density, expansion rate, and force strengths in our universe allowed it to avoid these fates, to expand and cool at just the right rate to allow structure to form later. Rest in the improbable gift of balanced existence. Whether this balance is a matter of chance, of selection from many possible universes, or of some deeper principle we have not yet discovered, remains one of the most intriguing open questions in cosmology. In this first instant that we can meaningfully speak about, the universe took its first breath. Space began to expand. Time began to flow forward. Gravity separated from the other forces and began shaping the geometry of space-time. The stage was set for all that would follow. The universe was still unimaginably hot and dense, still far from any condition we could directly observe or experiment with. But it had taken the first step away from the quantum void, had begun its journey toward complexity and structure, and eventually toward the rich cosmos we inhabit today. As we rest here, we might feel a sense of quiet awe at these beginnings, at the way something so simple and unified could contain within it the potential for everything that would later emerge. Float gently in this first awakening. Following the first instant of cosmic history, the universe entered a phase that would shape its large-scale properties in ways that still influence us today, more than 13 billion years later. This phase, called cosmic inflation, represents one of the most remarkable ideas in modern cosmology. A period of exponential expansion so rapid and so extreme that it stretches the imagination even of physicists who work with these concepts every day. Alan Guth proposed the inflationary model in 1980 to solve several puzzles about why the universe appears so uniform and geometrically flat, despite having no obvious reason to be that way. During a time interval that may have lasted only a tiny fraction of a second, perhaps 10 to the negative 32 seconds, the universe grew from submicroscopic size to something approaching the size of a grapefruit, or perhaps much larger depending on the details of how inflation proceeded. To understand why physicists proposed such an extraordinary idea, we need to consider some puzzles about the universe that earlier theories struggled to explain. The first of these puzzles involves the remarkable uniformity of the cosmos on large scales. Let this uniformity settle into your awareness. When we observe the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space, we find that its temperature is almost exactly the same in every direction we look, matching to within about 1 part in 100,000. The COBE satellite, launched in 1989, and later the WMAP and Planck missions, measured this uniformity with exquisite precision, confirming that the universe is far more homogeneous than we have any right to expect. This uniformity extends across regions of the sky that, according to the conventional Big Bang model, without inflation, should never have been in contact with each other, should never have had time to exchange energy and equalize their temperatures. How then did these distant regions end up at almost exactly the same temperature? The second puzzle concerns the geometry of space itself. Einstein's general relativity allows space to be curved in various ways. It could curve back on itself like the surface of a sphere, which is called positive curvature, or it could curve outward like a saddle, which is called negative curvature, or it could be perfectly flat with no curvature at all like an infinite sheet of paper. Breathe into the flatness of cosmic space. Observations indicate that our universe is flat, or very nearly flat to extraordinary precision. But flatness is an unstable condition in the conventional Big Bang model. A universe that started out even slightly curved would quickly become much more curved as it evolved. Robert Dick and James Peebles pointed out in the 1960s that the flatness of the universe requires incredibly fine-tuned initial conditions, with the curvature at early times set to within 1 part in 10 to the 60th power of the critical value. The fact that our universe is so close to flat today means it must have been extraordinarily, almost unbelievably flat in its earliest moments, which seems like a remarkable coincidence unless something caused it to be that way. The third puzzle involves the absence of certain exotic relics that many theories predict should have been created in the earliest moments of the universe. Some theories that attempt to unify the fundamental forces predict the existence of magnetic monopoles, particles that would carry isolated north or south magnetic poles, rather than the north-south pairs we observe in ordinary magnets. These monopoles should have been produced in enormous quantities in the early universe, so many that they would dominate the mass and energy density of the cosmos. Rest with the mystery of what is missing. Yet we have never detected even a single magnetic monopole, despite decades of searching. Something seems to have diluted these exotic particles to undetectable levels, or prevented them from forming in the first place. Cosmic inflation elegantly addresses all 3 puzzles through a single mechanism. The idea suggests that in the earliest moments after the Big Bang, the universe was filled with a special kind of energy associated with a field called the inflaton field. This field, similar in some ways to the Higgs field that gives particles their mass, was trapped in a high-energy state. False vacuum that contained enormous energy density but remained temporarily stable. While the inflaton field remained in this false vacuum state, it acted as a kind of anti-gravitational force, driving space to expand exponentially fast, doubling in size every tiny fraction of a second. During this inflationary expansion, any 2 points in space would rapidly separate from each other, with the distance between them growing exponentially. A region of space that started out smaller than an atom would expand to cosmic dimensions in an incredibly brief interval. Allow the expansion to unfold in your mind's eye. This explosive growth stretched space smooth, flattening out any initial curvature that might have existed, much like inflating a balloon smooths out wrinkles on its surface. It also stretched out any exotic particles like magnetic monopoles, diluting them so thoroughly that the probability of finding one in our observable universe became vanishingly small. Andre Linde developed the chaotic inflation model in the 1980s, showing that inflation could begin from a wide variety of initial conditions and naturally produce a flat, homogeneous universe. and it took a tiny patch of space that was initially in thermal contact, where all parts were at the same temperature, and stretched that patch so much that it eventually became larger than our entire observable universe. Explaining why the cosmic microwave background looks so uniform in all directions. The inflaton field could not remain in this high-energy, false vacuum state forever. Following the first instant of cosmic history, the universe entered a phase that would shape its large-scale properties in ways that still influence us today, more than 13 billion years later. This phase, called cosmic inflation, represents one of the most remarkable ideas in modern cosmology. A period of exponential expansion so rapid and so extreme that it stretches the imagination even of physicists who work with these concepts every day. Alan Guth proposed the inflationary model in 1980 to solve several puzzles about why the universe appears so uniform and geometrically flat, despite having no obvious reason to be that way. During a time interval that may have lasted only a tiny fraction of a second, perhaps 10 to the negative 32 seconds, the universe grew from submicroscopic size to something approaching the size of a grapefruit, or perhaps much larger depending on the details of how inflation proceeded. To understand why physicists proposed such an extraordinary idea, we need to consider some puzzles about the universe that earlier theories struggled to explain. The first of these puzzles involves the remarkable uniformity of the cosmos on large scales. Let this uniformity settle into your awareness. When we observe the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space, we find that its temperature is almost exactly the same in every direction we look, matching to within about 1 part in 100,000. The COBE satellite, launched in 1989, and later the WMAP and Planck missions, measured this uniformity with exquisite precision, confirming that the universe is far more homogeneous than we have any right to expect. This uniformity extends across regions of the sky that, according to the conventional Big Bang model, without inflation, should never have been in contact with each other, should never have had time to exchange energy and equalize their temperatures. How then did these distant regions end up at almost exactly the same temperature? The second puzzle concerns the geometry of space itself. Einstein's general relativity allows space to be curved in various ways. It could curve back on itself like the surface of a sphere, which is called positive curvature, or it could curve outward like a saddle, which is called negative curvature. Or it could be perfectly flat with no curvature at all, like an infinite sheet of paper. Breathe into the flatness of cosmic space. Observations indicate that our universe is flat, or very nearly flat to extraordinary precision. But flatness is an unstable condition in the conventional Big Bang model. A universe that started out even slightly curved would quickly become much more curved as it evolved. Robert Dick and James Peebles pointed out in the 1960s that the flatness of the universe requires incredibly fine-tuned initial conditions, with the curvature at early times set to within 1 part in 10 to the 60th power of the critical value. The fact that our universe is so close to flat today means it must have been extraordinarily, almost unbelievably flat in its earliest moments, which seems like a remarkable coincidence unless something caused it to be that way. The third puzzle involves the absence of certain exotic relics that many theories predict should have been created in the earliest moments of the universe. Some theories that attempt to unify the fundamental forces predict the existence of magnetic monopoles, particles that would carry isolated north or south magnetic poles, rather than the north-south pairs we observe in ordinary magnets. These monopoles should have been produced in enormous quantities in the early universe, so many that they would dominate the mass and energy density of the cosmos. Rest with the mystery of what is missing. Yet we have never detected even a single magnetic monopole, despite decades of searching. Something seems to have diluted these exotic particles to undetectable levels, or prevented them from forming in the first place. Cosmic inflation elegantly addresses all three puzzles through a single mechanism. The idea suggests that in the earliest moments after the Big Bang, the universe was filled with a special kind of energy associated with a field called the inflaton field. This field, similar in some ways to the Higgs field that gives particles their mass, was trapped in a high energy state. False vacuum that contained enormous energy density but remained temporarily stable. While the inflaton field remained in this false vacuum state, it acted as a kind of anti-gravitational force, driving space to expand exponentially fast, doubling in size every tiny fraction of a second. During this inflationary expansion, any 2 points in space would rapidly separate from each other, with the distance between them growing exponentially. A region of space that started out smaller than an atom would expand to cosmic dimensions in an incredibly brief interval. Allow the expansion to unfold in your mind's eye. This explosive growth stretched space smooth, flattening out any initial curvature that might have existed, much like inflating a balloon smooths out wrinkles on its surface. It also stretched out any exotic particles like magnetic monopoles, diluting them so thoroughly that the probability of finding one in our observable universe became vanishingly small. Andre Linde developed the chaotic inflation model in the 1980s, showing that inflation could begin from a wide variety of initial conditions and naturally produce a flat, homogeneous universe. And it took a tiny patch of space that was initially in thermal contact, where all parts were at the same temperature, and stretched that patch so much that it eventually became larger than our entire observable universe. Explaining why the cosmic microwave background looks so uniform in all directions. The inflaton field could not remain in this high-energy, false vacuum state forever. Eventually, through a process somewhat analogous to quantum tunneling, the field decayed to its lower energy, true vacuum state. When this happened, the enormous energy that had been stored in the inflaton field was released and converted into a hot bath of particles and radiation, reheating the universe and setting the stage for the more conventional Big Bang evolution that would follow. Drift into the transformation from expansion to heat. This transition from inflation to the hot Big Bang phase is called reheating, and it marked the end of the inflationary epoch and the beginning of a new phase, where the universe was filled with matter and radiation in thermal equilibrium. The quantum fluctuations that occurred during inflation would prove to have lasting significance. During the exponential expansion, even the tiniest quantum variations in the inflaton field itself were stretched from submicroscopic scales to cosmic proportions. These fluctuations meant that inflation ended slightly earlier in some regions of space and slightly later in others, leading to tiny differences in energy density from place to place. After inflation ended and the universe transitioned into the conventional expansion phase, these density variations became the seeds from which all cosmic structure would eventually grow. Regions that were slightly overdense would have slightly stronger gravity, attracting more matter and becoming even more overdense over time. Billions of years later, these tiny initial variations had grown into galaxies, clusters of galaxies, and the vast cosmic web of structure that we observe today. Observations of the cosmic microwave background have confirmed that the pattern of temperature fluctuations matches predictions from inflationary theory with remarkable precision. Rest in the seeds of everything that would come. You may imagine the universe during inflation as a kind of smooth, featureless expanse, growing faster than anything we encounter in everyday physics. No particles could form during this time because the expansion was so rapid that any particle created would immediately be swept away from everything else. No structures could assemble, no complexity could build, because the accelerating expansion overwhelmed any tendency for gravity to pull things together. The universe was simply stretching and growing, creating vast amounts of new space, smoothing itself out, preparing itself for the later phases when matter and radiation would fill space and begin the slower process of evolution and structure formation. The duration of inflation remains somewhat uncertain. Different versions of inflationary theory predict different timescales ranging from incredibly brief intervals to somewhat longer periods, though even the longer versions occupy only a tiny fraction of a second. What matters more than the precise duration is the amount of expansion that occurred. For inflation to solve the puzzles that motivated it, the universe needed to expand by a factor of at least 10 to the 26th power, and possibly much more. Breathe into the vastness of expansion. This means that every length scale increased by this enormous factor, which is more than enough to smooth out any initial curvature, dilute any exotic relics, and explain the uniformity we observe. The specific mechanism driving inflation likely involved physics at energy scales far beyond what we can reproduce in particle accelerators. The Large Hadron Collider, the most powerful accelerator ever built, can probe energy scales up to a few trillion electron volts. But inflation probably occurred at energy scales closer to 10 to the 15th trillion electron volts. Many orders of magnitude higher than anything we can directly test. This means that our detailed understanding of inflation must remain somewhat speculative, based on extrapolating our known physics to these extreme regimes and making educated guesses about what new physics might come into play. Despite these uncertainties, inflation has become a central part of modern cosmology because it makes specific predictions that we can test through observations. The quantum fluctuations stretched during inflation should have left an imprint in the cosmic microwave background radiation, creating a specific pattern of temperature variations across the sky. Float with the patterns written in ancient light. Observations of this pattern have confirmed key predictions of inflation, though they have not yet definitively ruled out alternative theories or distinguished between different versions of inflation. Inflation also predicts that gravitational waves should have been produced during this epoch, ripples in space-time itself that might still be detectable today as a faint signal in the polarization of the cosmic microwave background. Several experiments including BICEP, Keck-Array, and future space missions are currently searching for this gravitational wave signature, which would provide powerful confirmation of inflation and reveal details about how it occurred. As the universe inflated, it transformed from a quantum speck into a macroscopic expanse, from a region where quantum fluctuations dominated into a realm where classical physics began to apply. The expansion stretched space smooth and flat, erased any record of what came before, and set initial conditions that would influence everything that followed. In this way, inflation represents a kind of cosmic reset, a period that wiped clean whatever state the universe might have been in previously and established a new starting point from which the familiar hot Big Bang evolution could proceed. Rest in this moment of cosmic renewal. Some versions of inflationary theory suggest that inflation might not have ended everywhere at the same time. In these eternal inflation scenarios proposed by Andrei Lind and Alexander Vilenkin, while inflation ended in some regions like our observable universe, it continues in other regions, creating an ever-growing multiverse of bubble universes, each with potentially different physical properties. Our observable universe would be just one bubble among countless others, a finite region where inflation ended and allowed a hot Big Bang to begin. This idea raises profound questions about the nature of reality and the limits of what we can observe and understand. Whether or not eternal inflation is correct, the inflationary epoch that occurred in our cosmic history remains one of the most important periods to understand. In a tiny fraction of a second, it shaped the large-scale properties of our universe, determined its geometry, established the seeds of all structure, and set the stage for the 13 billion years of evolution that would follow. As we rest with this idea, we might feel the strangeness of it, the way something so brief could have such lasting consequences. Allow wonder to wash over you gently. The way quantum physics, operating at the smallest imaginable scales, could influence the shape of the cosmos across billions of light years. The universe expanded, stretched smooth, and prepared itself for the long journey ahead towards stars and galaxies and worlds where beings might eventually wonder about these origins. Underscore, 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 continued to cool. The expansion stretched the wavelengths of photons and other particles, reducing their energy, which manifests as a drop in temperature. Breathe with the cooling of the cosmos. This cooling was inexorable and steady, driven by the expansion itself. As the temperature dropped and approached a critical threshold around 2 trillion degrees, the universe underwent another important transition. The quark, gluon plasma could no longer remain in its deconfined state. Just as steam condenses into water when cooled, the quarks and gluons underwent a phase transition and began combining into hadrons, primarily protons and neutrons, along with other particles that would quickly decay into these stable forms. This transition from quark-gluon plasma to hadronic matter occurred throughout the universe, essentially simultaneously, when the cosmos was roughly 1 microsecond old. One moment, if we can speak of moments at such brief timescales, quarks swam freely in a hot gluon sea. The next moment, they had bound together into protons and neutrons, confined within these composite particles by the strong force. Lattice QCD calculations performed on supercomputers have allowed researchers to map out the phase diagram of strongly interacting matter and confirm that this transition occurs at temperatures around 2 trillion degrees. This phase transition was not gentle, but rather resembled a dramatic transformation, as the entire character of matter in the universe changed from deconfined quarks to confined hadrons. Rest in this moment of cosmic condensation. The physics governing this transition involves quantum chromodynamics, the theory of the strong nuclear force, which is notoriously difficult to calculate except in certain limiting cases. Physicists have used powerful computers to simulate quantum chromodynamics on discrete spacetime grids, an approach called lattice QCD, to study the quark-hadron phase transition. These calculations confirm that such a transition should occur at temperatures around 2 trillion degrees, and that it profoundly changes the properties of matter. They also suggest that the transition might have been a smooth crossover rather than a sharp first-order phase transition, meaning that the change from plasma to hadrons occurred rapidly, but without the kind of violent discontinuity that would have produced dramatic, observable consequences. You may imagine the universe during this transition as a vast hot soup suddenly organizing itself into more structured forms. Before the transition, quarks and gluons interacted in a chaotic fluid-like way with no persistent structure. After the transition, matter took on a more organized character, with quarks permanently confined inside protons and neutrons. These newly formed hadrons would become the building blocks of all atomic nuclei and eventually of atoms, molecules, and the rich chemistry that allows complex structures like stars and planets and living organisms to exist. Float through this moment of organization. The balance between matter and antimatter during this epoch deserves careful attention. In principle, the laws of physics, as we understand them, suggest that the Big Bang should have created equal amounts of matter and antimatter. Quarks should have been matched by antiquarks, electrons by positrons, and so forth. When matter meets its antimatter counterpart, they annihilate in a burst of energy, converting entirely back into photons. If the universe had contained exactly equal amounts of matter and antimatter, everything would have annihilated, leaving behind only a sea of photons with no matter at all. Yet clearly matter survived. The universe today contains galaxies and stars and planets made of matter with essentially no antimatter present, except for small amounts created in high-energy processes like cosmic ray collisions. Andrei Sakharov identified in 1967 the 3 conditions necessary for generating a matter-antimatter asymmetry, barrier number violation, charge parity violation, and departure from thermal equilibrium, all of which must have been satisfied in the early universe. This means that somehow a tiny asymmetry must have existed, a slight preference for matter over antimatter, amounting to perhaps 1 extra matter particle for every 10 billion matter-antimatter pairs. Let this imbalance settle into awareness. When the universe cooled enough, most of the matter and antimatter annihilated, but this small excess of matter remained. And it is this leftover material that makes up everything we see today. The origin of this matter-antimatter asymmetry, called baryogenesis by physicists remains one of the great unsolved problems in cosmology. The known laws of physics are almost perfectly symmetric between matter and antimatter, with only tiny violations observed in certain weak interaction processes. These known violations are not sufficient to explain the observed matter excess, suggesting that new physics beyond our current understanding must have operated in the early universe to generate the asymmetry. As the quark-gluon plasma transitioned into hadronic matter and the universe continued to cool, another important process began to occur: the weak nuclear force, which governs certain types of particle decay and transformation, allowed protons and neutrons to convert into each other through interactions with neutrinos and other particles. At high temperatures, these conversion processes occurred rapidly and kept protons and neutrons in thermal equilibrium, maintaining a particular ratio between them, determined by their slight mass difference and the ambient temperature. Drift with the shifting balance of particles. Neutrons are slightly heavier than protons by about 0.14%, so, as the universe cooled, the equilibrium ratio shifted gradually toward more protons and fewer neutrons. Eventually, when the universe cooled enough that these weak interaction processes became slow compared to the expansion rate, the neutron-to-proton ratio froze out, meaning it stopped changing even as the universe continued to cool. This freeze-out occurred when the universe was about 1 second old and left a ratio of roughly 1 neutron for every 7 protons. This ratio would prove crucial in the next phase of cosmic evolution, when neutrons and protons began combining to form the first atomic nuclei, because it determined what mix of elements would be produced in the early universe. During the quark epoch and into the hadronic phase, the universe also contained large numbers of other particles. Neutrinos, ghostly particles that barely interact with anything, filled space in enormous numbers and carried away energy as they free streamed through the cosmos. Rest in the abundance of unseen particles. Wolfgang Pauli first proposed the existence of neutrinos in 1930 to explain missing energy in beta decay, and they were finally detected directly in 1956 by Clyde Cowan and Frederick Reines through their interactions with protons. Electrons and their antimatter partners, positrons, were abundant and would remain so until the temperature dropped below the energy equivalent of their mass, at which point most of them would annihilate, leaving only the small excess of electrons needed to balance the charge of the surviving protons. Photons, particles of light, were by far the most numerous particles, outnumbering protons and neutrons by about 1 billion to 1. And they would remain the dominant form of energy in the universe for hundreds of thousands of years to come. As we rest with these ideas, we might sense the dynamic, almost violent nature of the early universe during this phase. The cosmos was a hot, dense, chaotic place where particles were constantly being created and destroyed, where matter and antimatter annihilated in floods of energy, where quarks combined and hadrons formed, where the character of matter itself was in flux. Allow the chaos to wash through you. Yet despite this chaos, the universe was following orderly physical laws, evolving in predictable ways that we can describe with mathematical precision. The transition from quark-gluon plasma to hadronic matter represents another step in the universe's journey from simplicity toward complexity, from undifferentiated energy toward the structured matter that would eventually fill the cosmos with stars and galaxies and worlds. As the universe continued its expansion and cooling, approaching the age of 3 minutes, conditions became ripe for another crucial transition. The temperature had dropped to around 1 billion degrees, still extraordinarily hot, but cool enough that atomic nuclei could begin to form and survive without being immediately torn apart by collisions with high-energy photons. This marked the beginning of an epoch called Big Bang nucleosynthesis, a brief but immensely important period when the first atomic nuclei heavier than hydrogen were forged from the primordial sea of protons and neutrons. Ralph Alpha, Hans Bethe, and George Gamow published their pioneering paper on nucleosynthesis in 1948, predicting the abundances of light elements that should have been produced in the early universe. The particular nuclei created during this time would set the stage for all subsequent chemistry and structure formation in the universe. The process began with the simplest possible nuclear reaction, the fusion of a proton and a neutron to form deuterium, an isotope of hydrogen containing 1 proton and 1 neutron in its nucleus. Drift into this first moment of atomic building. Deuterium is fragile and easily destroyed by high-energy photons, so it could not accumulate in significant quantities until the universe cooled enough that most photons lacked sufficient energy to break deuterium nuclei apart. This bottleneck delayed nucleosynthesis until about 3 minutes after the Big Bang, even though the temperature would have been favorable for deuterium formation somewhat earlier. Once the universe cooled past this threshold and deuterium could survive, it quickly became the stepping stone for building heavier elements. With deuterium available, a series of nuclear reactions proceeded rapidly. Deuterium nuclei could capture additional protons or neutrons, building up to helium-3, which contains 2 protons and 1 neutron, or tritium, which contains 1 proton and 2 neutrons. These isotopes could then combine in various ways to form helium-4, the common isotope of helium containing 2 protons and 2 neutrons, which is particularly stable due to its tightly bound nuclear configuration. Some of the helium-4 could capture additional neutrons to form helium-5, or combine with other helium or hydrogen nuclei to begin building toward even heavier elements, though these pathways quickly ran into difficulties. Rest in the limits of this early forging. The trouble with building elements heavier than helium-4 in the Big Bang is that there are no stable nuclei with mass number 5 or 8. Helium-5 is unstable and immediately falls apart, creating a gap that is difficult to cross. Beryllium-8, which you might form by combining 2 helium-4 nuclei, is also unstable and decays almost instantly with a lifetime of only 10 to the negative 16 seconds. Fred Hoyle famously predicted in 1953 that a resonance in carbon-12 must exist to bridge this gap during stellar nucleosynthesis, a prediction later confirmed experimentally and now known as the Hoyle state. These gaps in nuclear stability meant that the chain of nuclear fusion reactions that had worked well for building helium could not easily continue to build carbon and heavier elements. As a result, Big Bang nucleosynthesis produced essentially no elements heavier than lithium, the 3rd lightest element, which was created in trace amounts through alternative reaction pathways. By the time the universe was about 20 minutes old, nucleosynthesis had essentially ended. The temperature had dropped below the point where nuclei had enough thermal energy to overcome the electrical repulsion between protons and approach close enough for the strong nuclear force to bind them together. Allow the cooling to wash over you. The nuclear reaction stopped, and the mix of elements froze into the pattern that would characterize the universe for hundreds of millions of years to come, until the first stars formed and began producing heavier elements through their own internal fusion processes. The outcome of Big Bang nucleosynthesis was a universe composed by mass of roughly 75% hydrogen, 25% helium-4, and trace amounts of deuterium at about 25 parts per million, helium-3 at about 10 parts per million, and lithium-7 at about 10 parts per billion. This elemental composition has been preserved in the most pristine regions of the universe, in gas clouds that have never been enriched by material from stars. Careful measurements of these abundances provide one of the most powerful tests of Big Bang cosmology. The predicted abundances match observations remarkably well, giving us confidence that we understand this epoch in considerable detail. David Schramm and colleagues refined nucleosynthesis calculations in the 1970s and 80s, showing that the observed abundances could constrain the density of ordinary matter in the universe with surprising precision. Breathe with the validation of understanding. You may picture the universe during nucleosynthesis as a vast nuclear furnace, though a rapidly cooling one. For a brief window of time, conditions resembled those in the cores of stars, where nuclear fusion releases energy that makes stars shine. But unlike stellar cores, where fusion continues for millions or billions of years at a steady rate, the Big Bang nuclear furnace operated for only about 15 minutes before the expansion carried the temperature below the threshold for fusion to continue. In that brief interval, roughly 1/4 of all the protons in the universe were converted into helium, locked into nuclei that would remain intact for billions of years. The ratio of helium to hydrogen produced during this time depends sensitively on several factors, particularly the density of protons and neutrons at the time of nucleosynthesis and the neutron-to-proton ratio that had frozen out about 2 minutes earlier. A universe with higher density would have allowed more efficient conversion into helium, while lower density would have left more material as hydrogen. The observed helium abundance, combined with measurements of deuterium and lithium, allows cosmologists to determine the density of ordinary matter in the universe with remarkable precision. Float in this convergence of prediction and observation. These measurements reveal that ordinary matter, the protons, neutrons, and electrons that make up atoms, comprises only about 5% of the total energy content of the universe, with the remainder consisting of dark matter and dark energy, mysterious components that we detect through their gravitational effects but do not yet fully understand. The nuclei formed during Big Bang nucleosynthesis would not become complete atoms for a long time. At temperatures above a few thousand degrees, any electron that tried to bind to a nucleus would quickly be knocked free again by energetic photons, so matter remained ionized, existing as a plasma of free nuclei and electrons rather than neutral atoms. This ionized state would persist for hundreds of thousands of years until the universe cooled enough for recombination to occur, the process where electrons and nuclei finally combined to form stable neutral atoms. The success of Big Bang nucleosynthesis as a theory provides powerful evidence for the hot Big Bang model itself. When physicists first calculated what mix of elements should be produced in the early universe, they made specific quantitative predictions that could be tested through observations. Rest in the triumph of understanding. The fact that measurements of helium, deuterium, and lithium abundances match the predictions so well, when these predictions were made decades before the measurements were possible, represents one of the great triumphs of modern cosmology. It tells us that we really do understand what the universe was like when it was only a few minutes old, that our theories of nuclear physics and cosmology are capturing something real about how the cosmos evolved. Some questions remained even after the success of Big Bang nucleosynthesis. The lithium abundance predicted by the theory seems to be about 3 times higher than what is observed in the oldest stars, a discrepancy known as the cosmological lithium problem. Several explanations have been proposed, including the possibility that stars destroy some of their primordial lithium through internal mixing processes, or that some new physics affected lithium production in the early universe, or that our measurements are more complicated than we realize. This puzzle keeps researchers engaged, reminding us that even well-established theories can hold surprises, and that mysteries remain even in epochs we thought we understood. As the universe emerged from the nucleosynthesis epoch, it had taken another important step in its evolution from simplicity toward complexity. Drift with this step toward richness. The primordial soup of free protons and neutrons had been partially converted into helium and trace amounts of other light elements, establishing the chemical foundation upon which all later complexity would be built. These nuclei would eventually become the raw material for the first stars, and the hydrogen left over would fuel billions of generations of stellar fusion, gradually enriching the cosmos with the full range of elements found on the periodic table. In this quiet moment after nucleosynthesis, we might sense the calm that descended as the nuclear reactions ceased, and the universe entered a long period of cooling and expansion. The dramatic phase transitions were over for now. The cosmos would spend the next several 100,000 years in a relatively uneventful state, gradually cooling from billions of degrees to thousands of degrees, allowing matter and radiation to slowly fall out of thermal equilibrium, preparing for the next major transformation when atoms would form and light would finally stream freely through space for the first time. The nuclei created in those first 20 minutes would wait patiently for their electrons to arrive, for chemistry to become possible, for stars to light up and begin the long work of building heavier elements that would eventually allow planets and life to exist. Rest in the patient waiting of matter. For hundreds of thousands of years following nucleosynthesis, the universe continued its steady expansion and cooling, entering a phase that cosmologists call the photon epoch, a long period dominated by the energy of radiation rather than matter. This stretching reduced the energy of each photon, which manifests as a drop in temperature. By the time the universe reached an age of about 380,000 years, the temperature had cooled to around 3,000 degrees, comparable to the surface temperature of a red star. At this temperature, something important changed. Photons no longer had enough energy to ionize hydrogen atoms by knocking their electrons free. Breathe into this threshold of transformation. Electrons could now bind to protons and remain bound, forming stable neutral hydrogen for the first time since the first moments after the Big Bang. The transition from ionized plasma to neutral atoms occurred quite rapidly throughout the universe, perhaps over a span of about 100,000 years, which is sudden compared to the age of the cosmos at that time. This process is called recombination, though the name is somewhat misleading since the electrons and nuclei had never been combined before to be recombined. Nevertheless, the term has stuck in the cosmological literature, and it marks one of the most important milestones in cosmic history. As electrons bound to nuclei and formed neutral atoms, the free electrons that had been scattering photons disappeared, and the universe quite suddenly became transparent to light. The photons that had been trapped, constantly scattering off free electrons and unable to travel far without hitting something, suddenly found themselves in a transparent universe where they could stream freely through space without obstruction. Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background in 1964 while working on satellite communications, detecting a faint microwave glow coming from all directions in the sky with a temperature of about 3 degrees above absolute zero. Rest in the liberation of ancient light. These photons, which had been in thermal equilibrium with matter now decoupled from matter, and began their journey through the expanding cosmos, traveling unimpeded for billions of years. The photons we detect today as the cosmic microwave background radiation are precisely these ancient photons, released when the universe became transparent, now stretched by cosmic expansion from their original wavelengths in the visible and infrared parts of the spectrum to microwave wavelengths. You may imagine the moment of recombination, as the universe transforming from a glowing fog to crystal clarity. Before, every direction you looked would show the glow of hot plasma, like being inside a luminous cloud. After, you would see darkness punctuated only by the faint afterglow of the recombination itself, and much later, when stars formed, by the light of those distant stars. This transition represented the universe's first clear view of itself, the moment when light could finally travel across vast distances and carry information about what the cosmos looked like at different times and places. The cosmic microwave background radiation that we observe today provides an incredibly detailed snapshot of what the universe looked like at the moment of recombination. Drift through this ancient portrait. By carefully measuring the temperature of this radiation across the entire sky, cosmologists have created maps that show tiny variations in temperature from place to place, differences of only about 1 part in 100,000. These temperature variations reflect density variations that existed in the universe at the time of recombination. Regions that were slightly denser appeared slightly cooler in the cosmic microwave background because photons climbing out of their gravitational wells lost energy in the process. An effect predicted by general relativity called gravitational redshift, while photons from slightly less dense regions appeared slightly warmer. These tiny density variations, imprinted in the cosmic microwave background, were the seeds from which all structure in the universe would eventually grow. The regions that were slightly overdense at recombination had slightly stronger gravity, which attracted more matter over time. As the universe continued to expand and cool, these overdense regions would grow more pronounced, eventually collapsing under their own gravity to form the first stars, galaxies, and galaxy clusters. In this way, the pattern we see in the cosmic microwave background represents a baby picture of the universe, showing the initial conditions from which everything we observe today ultimately developed. Allow these seeds to settle in your mind. The physics of recombination involves some subtleties worth considering. Hydrogen atoms can exist in different energy levels, with the ground state being the lowest energy configuration and various excited states representing higher energy configurations where the electron orbits farther from the nucleus. Direct recombination into the ground state produces a high-energy photon capable of immediately ionizing another hydrogen atom, which does not help build up a population of neutral hydrogen. The most efficient path to recombination involves electrons first capturing into high excited states, then cascading down through intermediate levels before reaching the ground state. This process produces lower energy photons at each step that are less likely to ionize other atoms, allowing the neutral fraction to build up gradually. Yakov Zeldovich, Vyacheslav Mukhanov, and Rashid Sunyaev worked out the detailed physics of recombination in the 1960s and 70s, showing that the process occurs over an extended period rather than instantaneously and leaves subtle signatures in the spectrum and polarization of the cosmic microwave background. Another player in the recombination story is helium, which actually recombined before hydrogen because helium is more tightly bound and therefore requires less cooling before electrons can stably attach to its nuclei. Breathe with the layered unfolding of atoms. Helium recombination occurred in two stages. First, when helium captured one electron to become singly ionized helium, and later when it captured a second electron to become neutral helium. These helium recombination events occurred at slightly higher temperatures than hydrogen recombination and left their own subtle signatures in the cosmic microwave background that cosmologists can detect and study. After recombination was complete, the universe entered a new phase sometimes called the Dark Ages, because with no stars yet formed and the cosmic microwave background fading into the infrared, and then microwave parts of the spectrum as the universe continued to expand, there were no sources of visible light. The cosmos was filled with neutral hydrogen and helium gas slowly condensing under gravity into larger and larger clumps that would eventually become dense enough to ignite nuclear fusion and light up as the first stars. This process would take another 100 million years or so, meaning the Dark Ages represent a substantial fraction of early cosmic history. During the Dark Ages, though no light sources existed, the universe was not static. The density perturbations that had been growing slowly since the end of inflation were now able to grow more rapidly because matter, no longer kept smooth by interactions with radiation, could clump together under gravity without resistance. Float in the quiet gathering of matter. Dark matter, which does not interact with photons and had been free to clump since much earlier times, had already formed extensive structures by the time of recombination. Ordinary matter, now neutral and transparent, began falling into the gravitational wells created by dark matter concentrations, gathering in the densest regions and setting the stage for star formation. As we rest with these ideas, we might appreciate the patience required in cosmic evolution. From the violent first moments of inflation and the hot plasmas of the early universe, the cosmos gradually cooled and calmed, taking hundreds of thousands of years to reach the point where atoms could form and light could travel freely. This represents a fundamental transition from a universe dominated by radiation and plasma physics to one dominated by matter and gravity, from a smooth, featureless state to one where structure could begin to grow, from opacity to transparency, from uniformity to the rich variety that would later characterize the cosmos. The photons released at recombination have been traveling through space ever since, carrying with them information about the conditions in the universe at that time. As space expanded, these photons were stretched to longer and longer wavelengths, cooling from the thousands of degrees they had when released to the mere 3 degrees above absolute zero that they possess today. Rest in the journey of light across time. When cosmologists measure the cosmic microwave background, they are literally seeing the universe as it was 380,000 years after the Big Bang, observing photons that have traveled for more than 13 billion years to reach our telescopes, preserved almost unchanged, except for the redshift imposed by cosmic expansion. The detailed measurements of the cosmic microwave background have revolutionized cosmology, allowing researchers to determine the age of the universe at 13.8 billion years, its composition with about 5% ordinary matter, 27% dark matter, and 68% dark energy, its geometry which is flat to within measurement precision, and many other fundamental properties. The patterns of temperature variation encode information about the density of matter, the density of dark energy, the rate of expansion, the curvature of space, and even the initial quantum fluctuations generated during inflation. By analyzing these patterns, cosmologists have constructed a standard model of cosmology that describes the universe's history from the first fraction of a second through the present day, tested against a wealth of observational data, and found to be remarkably consistent. As recombination ended and the cosmic microwave background, photons began their long journey through space, the universe transitioned into a new era. Allow this transition to wash through you. The dramatic phase transitions were over. The basic constituents of matter had been established, and the initial conditions for structure formation had been set. What remained was the long, slow work of gravity pulling matter together, of density perturbations growing into stars and galaxies, of the first light sources illuminating the darkness, and eventually of planets forming and life emerging on at least one of those planets to look back and try to understand this remarkable story of cosmic origins. The cosmic story continues whether you wake or sleep, whether you observe or rest. The universe will keep expanding. Stars will keep shining. Matter will keep evolving according to the elegant laws of physics. And in the morning when you wake, you will be part of that ongoing story once more, conscious and aware and capable of wonder. But for now, let all of that go. Let the cosmic perspective fade into gentle darkness. Let the billions of years and trillions of galaxies dissolve into simple rest. Sleep now in cosmic peace, knowing you are home in the universe that made you. After the universe became transparent at recombination, it entered a long, quiet period that astronomers call the cosmic dark ages, a time when the afterglow of the Big Bang had faded into infrared wavelengths and no stars yet existed to provide new sources of light. For perhaps 100 million years, the universe expanded in darkness, filled with neutral hydrogen and helium gas slowly gathering under gravity's patient pull, preparing for the dramatic moment when the first stars would ignite and illuminate the cosmos for the first time since recombination. This epoch represents a fascinating transition between the simple uniform state revealed in the cosmic microwave background and the complex structured universe we observe today. During the Dark Ages, the universe was not static, but rather undergoing important changes, though these changes occurred slowly by the standards of earlier epochs. The density perturbations that had been imprinted during inflation and encoded in the cosmic microwave background continued to grow as gravity amplified the initial variations. Drift into this slow, patient gathering. Regions that were slightly overdense attracted matter from their surroundings, becoming more overdense over time, while regions that were slightly underdense lost matter to denser regions and became increasingly empty. This process, called gravitational instability, represents the fundamental mechanism by which cosmic structure grows from tiny initial variations into the galaxies and clusters we observe today. James Jeans worked out the basic theory of gravitational instability in 1902, showing that a gas cloud will collapse under its own gravity if it exceeds a critical mass that depends on its temperature and density, a threshold now called the Jeans mass. The growth of structure during the Dark Ages occurred primarily in the dark matter component, which comprises about 85% of the matter in the universe by mass. Dark matter, whatever it may be, does not interact with light and barely interacts with ordinary matter except through gravity. This means it was free to clump together under gravity without any resistance from radiation pressure or other forces that affect ordinary matter. By the time ordinary matter became neutral at recombination and could also begin clumping, dark matter had already formed an extensive cosmic web of filaments and halos, gravitational structures into which ordinary matter would fall and concentrate. Rest in the invisible scaffolding of the cosmos. You may picture the universe during this time as a vast network of invisible scaffolding built from dark matter, with ordinary matter beginning to flow along this scaffolding like water running down into valleys. The densest dark matter halos, regions where dark matter had concentrated most strongly, exerted the strongest gravitational pull and attracted the most ordinary matter. These were the sites where the first stars would eventually form, in the hearts of the deepest gravitational wells, where gas could compress to high enough density and temperature to ignite nuclear fusion. The process by which gas cooled and condensed in these dark matter halos involved some interesting physics. As gas falls into a gravitational well, it gains kinetic energy and heats up, a process called gravitational heating. For gas to continue collapsing and concentrating rather than being supported by this thermal pressure, it needs to radiate away the heat it gains from falling inward. In the present-day universe, gas can cool efficiently through many processes. But in the dark ages, with the universe composed almost entirely of hydrogen and helium, cooling mechanisms were limited. Allow the slow cooling to settle into you. Hydrogen atoms can cool by exciting their electrons to higher energy levels and then emitting photons as the electrons fall back down. But this process is not particularly efficient at the temperatures and densities present in the early universe. A more important cooling mechanism came from molecular hydrogen. Two hydrogen atoms bound together into a molecule. Molecular hydrogen can rotate and vibrate, and transitions between different rotational and vibrational states can emit photons that carry away energy, allowing the gas to cool. Even though molecular hydrogen formed in only tiny amounts, perhaps one molecule for every 100,000 hydrogen atoms, it provided just enough cooling to allow the densest gas clouds to collapse and concentrate. Tom Abel and colleagues performed detailed computer simulations in the late 1990s, showing how the first gas clouds cooled through molecular hydrogen emission and collapsed to form the first stars in dark matter halos, with masses around 1 million times the Sun, eventually reaching conditions where stars could form. The first stars, sometimes called population, 3 stars to distinguish them from later generations, would have been quite different from typical stars in the present-day universe. Because they formed from gas composed almost entirely of hydrogen and helium with essentially no heavier elements, they could not cool as efficiently as later stars that formed from enriched gas containing carbon, oxygen, and other elements produced by previous generations of stars. Breathe into the birth of first light. Less efficient cooling meant that the first gas clouds that collapsed to form stars tended to be more massive than typical stellar masses today, perhaps tens or even hundreds of times the mass of our Sun. These massive first stars would have been extraordinarily luminous and hot, with surface temperatures exceeding 50,000 degrees and luminosities millions of times that of the Sun, burning through their nuclear fuel rapidly and living for only a few million years before exploding as supernovae. Their intense ultraviolet radiation would have begun to reionize the hydrogen gas surrounding them, creating bubbles of ionized gas that expanded outward as more stars formed and contributed their radiation. This process marks the end of the Dark Ages and the beginning of a new epoch called the Epoch of Reionization, when the universe transitioned from being mostly neutral to being mostly ionized once again, though in a very different configuration than the smooth, uniform ionization that existed before recombination. The exact timing of when the first stars formed remains somewhat uncertain. Current estimates suggest it occurred somewhere between 100 and 200 million years after the Big Bang, with the epoch of reionization lasting several hundred million years as more and more stars and early galaxies formed and their collective radiation gradually ionized the intergalactic medium. Float through the gradual awakening of light. Observations are beginning to probe this era using powerful telescopes like the James Webb Space Telescope, launched in 2021 to detect the faint light from some of the first galaxies, systems of millions or even billions of stars that formed from the collapse of large gas clouds in massive dark matter halos. One challenge in studying this epoch is that the neutral hydrogen gas that filled the universe during the Dark Ages absorbs ultraviolet light very efficiently. This means that light from the first stars and galaxies, which was emitted in the ultraviolet part of the spectrum, was absorbed by the intervening neutral hydrogen before it could reach us. Only after reionization was well underway, and most of the hydrogen between galaxies had been ionized, could ultraviolet light travel freely through the universe. For this reason, direct observations of the very first stars remain extremely difficult, though astronomers are developing increasingly sophisticated techniques to study this era indirectly through measurements of the cosmic microwave background, the distribution of heavy elements in old stars, and the properties of distant quasars whose light has traveled through the reionizing universe. As we consider the Dark Ages and the epoch of reionization, we might sense the transformation occurring in the nature of the universe. Rest in this great transformation. During the Dark Ages, the cosmos was entering a new phase where gravity dominated the evolution of structure, where the smooth initial conditions revealed in the cosmic microwave background were giving way to increasingly pronounced density contrasts. The first stars represented a profound transition, the moment when the universe, having been powered by the afterglow of the Big Bang for hundreds of thousands of years, began generating new sources of light and energy through nuclear fusion in stellar cores. The heavy elements produced by the first stars, carbon and oxygen and iron and many others, would be dispersed through space when these stars exploded as supernovae, enriching the surrounding gas with the raw materials needed for planets and eventually for life. This chemical enrichment would make subsequent generations of stars more diverse, with some stars, forming from enriched gas being smaller and longer, lived than the massive first stars, allowing a wider range of stellar types to populate the universe. The periodic table of elements was built up gradually over billions of years through nucleosynthesis in stellar cores and supernova explosions, with each generation of stars adding more heavy elements to the cosmic mix. The cosmos was becoming more complex, more diverse, more interesting with each passing generation of stars. Allow this enrichment to flow through you. The structures that formed during the Dark Ages and early epochs would eventually grow into the galaxies we observe today. Small proto-galaxies merged together to form larger systems, driven by the gravitational attraction between their dark matter halos. The cosmic web that had begun as tiny quantum fluctuations during inflation had grown into density variations visible in the cosmic microwave background, and had further developed during the Dark Ages, would continue evolving, with galaxies flowing along filaments and concentrating in clusters at the intersections of those filaments, while vast voids remained nearly empty of galaxies. Computer simulations like the Millennium Simulation, run in 2005, and the more recent Illustris TNG project have traced this cosmic evolution from early times to the present, showing how gravity sculpts matter into the hierarchical web-like structure we observe. As reionization progressed and more galaxies formed, the universe began to take on a character more similar to what we observe today. Stars provided new sources of light, galaxies assembled into larger structures, and the intergalactic medium, the gas between galaxies, remained mostly ionized due to the ongoing radiation from stars and other energetic sources. Breathe with the slow assembly of galaxies. Yet even with these developments, the universe was still very young, still in the process of building the structures that would eventually include our own Milky Way galaxy and the solar system and Earth, and all the life that has emerged on our planet. The transition from the Dark Ages to the epoch of reionization to the structured universe we observe today took billions of years to complete fully. Each stage built upon what came before, with simple initial conditions gradually evolving into increasing complexity through the action of gravity, star formation, chemical enrichment, and the ongoing expansion of space. As we rest with this understanding, we might appreciate the deep continuity in cosmic history, the way the universe has been on a long journey from simplicity toward complexity, from uniformity toward structure, from darkness toward light. The first stars have long since died, their light scattered and their constituent atoms dispersed and incorporated into later generations of stars and planets. Yet their legacy remains in the enriched gas they left behind, in the ionized medium their radiation created, and in the gravitational structures their host dark matter halos helped build. Float in the legacy of ancient light. They represent the beginning of the luminous universe we inhabit, the moment when the cosmos transitioned from darkness into an era of stars and galaxies that would continue evolving and changing for billions of years to come, creating the conditions that would eventually allow beings like us to emerge and wonder about these distant beginnings. In the quiet darkness before the first stars, in the slow gathering of gas in gravitational wells, in the patient work of gravity, amplifying tiny initial perturbations into structures massive enough to ignite fusion, we can see the universe preparing itself for all that would follow. The Dark Ages were not empty or meaningless, but rather a crucial transition period. A time when the foundations were laid for the rich cosmic ecosystem that would later flourish. As this epoch came to an end and the first light pierced the darkness, the universe entered a new chapter in its long continuing story. A story that includes our own origins and invites us to keep exploring, keep questioning, keep seeking to understand our place in this vast, ancient, still unfolding cosmos that began in quantum potential and blossomed into the light and structure and wonder we see around us today. Rest now in the quiet awe of understanding. Allow yourself to drift through the long story of the universe, from the quantum void before time, through the first instant of separation and expansion, through the inflationary stretching that smoothed space and planted the seeds of structure, through the hot plasma of quarks and gluons that condensed into protons and neutrons, through the brief nuclear furnace that forged the first elements, through ever-long photon epoch and the moment of recombination when light broke free, through the patient dark ages when gravity slowly gathered matter into the first stars. All of this, the entire sweep of cosmic history from nothing to something, from simplicity to complexity, from uniform glow to rich structure, unfolded according to natural laws that we can study and understand. Laws written in the language of mathematics and physics, laws that connect the smallest quantum fluctuations to the largest structures in the universe, laws that allowed matter to organize itself into stars and planets, and eventually into living beings capable of looking back across billions of years and comprehending their own origins. Let yourself rest in this cosmic story. You are made of atoms forged in the hearts of ancient stars, atoms that were once part of the primordial hydrogen created minutes after the Big Bang. Atoms that trace their lineage all the way back to the quantum fluctuations in the inflaton field during the first tiny fraction of a second. The calcium in your bones, the iron in your blood, the carbon in your cells, All of it was created through cosmic processes that began with the simplest possible ingredients and gradually built up the complexity needed for life through billions of years of stellar alchemy. You are not separate from the cosmos, but a part of it, a way for the universe to know itself, to reflect on its own history, to wonder about its origins and its future. As you drift towards sleep, let this cosmic perspective settle gently into your awareness. You are resting in a universe that is 13.8 billion years old, a universe that began in unimaginable simplicity and has been growing in complexity ever since. A universe vast, almost beyond comprehension, yet governed by elegant mathematical laws that our minds can grasp. Allow this knowledge to bring peace. The same physical processes that shaped the early universe continue today. Stars are still forming, still fusing hydrogen into helium and heavier elements, still enriching the cosmos with the building blocks of planets and life. Galaxies are still growing through mergers and accretion, still tracing out the cosmic web established by quantum fluctuations 14 billion years ago. Space itself is still expanding, carrying distant galaxies ever farther away, continuing the journey that began in the first instant after the quantum void. And in this vast cosmic unfolding, on one small planet orbiting an ordinary star in an unremarkable galaxy, conscious beings emerged who could look up at the night sky and ask questions about where it all came from. Who could build instruments to detect the faint whisper of light from the moment of recombination. Who could develop theories to describe what happened in the first fraction of a second. Who could piece together this remarkable story of cosmic origins and find their place within it? Rest in your place within the story. Let yourself float now in the gentle darkness, knowing that the darkness around you connects to the cosmic dark ages, to the period before the first stars, when the universe waited patiently for light to return. Knowing that the atoms in your body connect you to the nuclear furnace of the early universe and to the cores of ancient stars. Knowing that the space around you, seemingly empty, is actually the same space that inflated from quantum foam, that curved under the weight of matter and energy, that allowed light to travel across billions of years to reach our telescopes. You are part of this cosmos, this vast ancient story of matter and energy, organizing itself into ever more complex and beautiful forms. As you drift towards sleep, let this cosmic context embrace you. Let the billions of years of cosmic evolution that led to this moment wash over you like a gentle wave. Let the patience of gravity slowly gathering matter, the persistence of light streaming through expanding space, the gradual enrichment of the universe with heavier elements, all of it remind you that you are part of something much larger and older than yourself. Drift now into cosmic rest. The universe is still expanding, still evolving, still creating new stars and perhaps new worlds where other beings might someday wonder about their origins just as you have. The story that began in quantum potential continues to unfold, and you are part of that unfolding. A brief local eddy in the cosmic flow where matter became conscious and aware and capable of understanding its own history. Sleep now in this knowledge. Sleep in the embrace of cosmic time and space. Sleep knowing that the same laws that shaped the early universe continue to operate, that the same matter and energy that filled the primordial cosmos now fills you. Let your breath slow and deepen like the cooling of the early universe. Let your thoughts settle like matter condensing in gravitational wells. Let yourself drift through the long cosmic story, from quantum void to first instant to inflationary expansion to hot plasma to nucleosynthesis to the photon epoch to recombination to the dark ages to the first stars. Let this journey carry you gently into sleep, into rest, into the quiet darkness that connects you to the darkness before light, to the patient waiting before stars. Rest now in cosmic peace. The universe has been journeying for 13.8 billion years, and it will continue for billions more. In this vast sweep of time, your rest is a small but meaningful moment, a pause in the cosmic unfolding, a moment of consciousness returning to quiet, of complexity settling into simplicity, of wakefulness dissolving into sleep. Let yourself be carried by this cosmic current. Let the weight of billions of years of evolution support you. Let the vastness of space embrace you. You are made of stardust, made of atoms forged in cosmic furnaces, made of matter that has existed since the first moments after the Big Bang. You are the universe experiencing itself, knowing itself, resting itself. Sleep now in this cosmic embrace. Sleep in the gentle certainty that you are part of something vast and ancient and beautiful. Sleep knowing that the same forces that shaped galaxies and stars also shape your breath, your heartbeat, your dreams. Float into the cosmic night. Let the darkness around you become the cosmic dark ages, the patient waiting before light. Let the silence around you become the silence before the first sound waves could propagate through cooling plasma. Let the stillness around you become the stillness of the quantum void before time began. You are resting in a universe that began in simplicity and has been growing in complexity for billions of years, and in your rest, you return briefly to that simplicity, that quiet, that peace.